radiation. Okay, suppose if you want to get this what we call electromagnetic radiation, then we have to uh, accelerate these charges. So if you accelerate these charges, you are going to get this electromagnetic radiation. That means the stationary charges produces the electric fields, whereas the uniformly moving charges are going to be produce the electromagnetic fields. They are going to be produced, and whereas if these charges are accelerated, then it is going to be produce this electromagnetic radiation. And moreover, this electromagnetic radiation, whichever it is going to be produced with respect to the time, that is nothing but the time varying magnetic fields, they are going to be create the electric field and as well as the magnetic field. And these accelerated charges are going to be produced the what we call electromagnetic radiation. And these electromagnetic radiation, which is having very so many applications, like in the radiation of this electromagnetic radiation will be having so many applications. So the applications will later we are going to be see, but initially we are going to be see about the what is the wave equation which is going to be arise with the help of these electromagnetic field. So in order to get this inhomogeneous wave equation, we are going to be see about the Maxwell's equations, and from the Maxwell's equations we are going to be get these electromagnetic wave equation with the help of this electric potential as well as the vector potential. From with the help of these, we are going to be arise this homogeneous wave equation. So now we'll see this homogeneous wave equation, then we'll move to different topics in this. Okay, so first we'll do is now we'll see here 1 minute. So first we will so in this electromagnetic radiation, in this electromagnetic radiation, so it in this electromagnetic radiation, first we are going to be see what is the inhomogeneous wave equation. So we will see inhomogeneous wave equation we are going to see here. So later on we'll see different equations here. So in this homogeneous equation, in order to arrive this homogeneous wave equation of this, we'll take all the four Maxwell's equations we are going to write. the first Maxwell's equation which we have is del dot E. Okay, so this del dot E is equals to rho by epsilon naught. So this is first Maxwell's equation we have. Then we have the second Maxwell's equation is del dot B is equals to 0. Third Maxwell's equation, that is del cross E is equals to rho B by rho T we are going to be have. And the fourth Maxwell's equation is del cross B. Okay, this is del cross B, which will be equals to, we can write it as a mu naught J plus, we can write mu naught epsilon naught dou E by dou T we are going to write. So these are the four Maxwell's equations which we have. So with the help of these four Maxwell's equation, we will be considering two Maxwell's equation which satisfies the otherwise by introducing the what we call vector potential and scalar potential, we will take the second Maxwell's equation and as well as the Maxwell's equation. With the help of these two Maxwell's equation, we can write B is equals to del cross A, we can write. Okay, B is equals to del cross A, we can write. And also we know that another equation which is E is equals to minus del phi, okay, plus, sorry, minus dou A by dou T. Okay, so these are the two equations which we are introducing, that second Maxwell's equations and third Maxwell's equation identically satisfied by the introducing what we call potentials. One is scalar vector potential A and scalar potential phi we can have. And then what will we do is we are going to be take this B is equal to del cross A and E is equal to minus del phi minus dou A by dou T. So we will substitute these potentials A and phi in the equation of 1 and 4, that is Maxwell's equation. One is del dot E is equal to rho by epsilon naught, and fourth Maxwell's equation is we have like a del cross B is equal to mu naught J plus mu naught epsilon naught dou E by dou T. In those equations, we are going to be substitute here. So here, if you write the first Maxwell's equation, which is actually we have del dot E is equals to rho by epsilon naught is there. So here, what we'll do is here in place of this E, we are going to be substitute this value, that is minus del phi minus dou A by dou T. So therefore, it will become so del of dot minus del phi minus dou A by dou T, which will be equal to rho by epsilon naught. So this is what we have. Okay. And then what we'll do is here. If you multiply with this, that is minus del into minus del phi. So we are going to get it as a del square. We will get as a minus del square phi by, but we'll remove that minus so that we are going to get it as a plus dou by dou T of next you are going to get it as a del dot A, and which will be equals to minus rho by epsilon naught. So this equation, just we have multiplied this del dot del phi, so that we got del square phi. Actually, we should get minus minus we have taken outside. So del square phi plus dou A by dou T of del dot A is equals to minus rho by epsilon naught we have. Okay. So this one we have got. Now again, what we'll do is we will substitute this E value, that is minus del phi by del phi minus dou A by dou T in the equation, what we call another equation. So that is E is equal to minus del phi minus dou A by dou T in the equation of del cross B. This equation, in this equation, we are going to be substitute. So this is one equation which we are getting. So you take it as equation 2, we are going to be taken, and then we'll substitute that in the third equation. That is what we have is del cross, in place of B, we are substituting del cross A. So it will be del cross of del cross A, which will be equals to, already we have on the RHS mu naught J plus mu naught epsilon naught is there, and here what we have is dou E by dou T. So therefore, in place of E, we will substitute the dou by dou T, and in place of E, it will be minus del phi minus dou A by dou T. Here we are going to get. Okay. So now here on the LHS, we have a del cross of del cross A. So by using the vector identity formula, that is del cross A is equals to what we are going to get is, here we'll use vector identity. So by using the vector identity, so this del cross A will becomes del cross this by using this one del cross A, it will becomes equals to del of del dot A minus, next we have del square A we are going to get. So by using the vector identity, and also we'll use this on the RHS, which we have on this RHS we have mu naught epsilon naught. In place of mu naught epsilon naught, by using the wave equation, we will take as mu naught epsilon naught is equals to 1 by c square. We are going to be right. So now these two values, this value, we are substituting here. So if you substitute there, so in place of del cross A, we are going to be substitute as a del of del dot A. We are going to be substitute minus del square A, which will be equals to, on the RHS we have in that equation as mu naught J. This will be there, and in place of mu naught epsilon naught, we are substituting 1 by c square. We are substituting 1 by c square. Then we have this dou by dou T of minus del phi minus dou A by dou T. So this we are writing it as a minus of minus already we have. So we are writing this as del of dou phi by dou T. So del, it will become del of dou phi by dou T, it will become, and again this 1 by c square we are substituting inside another term. In that it will be minus 1 by c square into, it will be dou square A by dou T square. That means, so this we are multiplying with this one, and we are multiplying with this one along the values of this. Okay. So now if you solve this equation, it will be, what I'll do is I'll write this del square to this side. So it will be plus del square A, and this will be a minus 1 by c square. Another term which we have is minus dou square A by dou T square, and minus of, so this del we are taking to that side, so it will be minus of del of del dot A plus 1 by c square into del of dou phi by dou T, which is so this by taking the all Maxwell's equations, which we have got one equation as a del square phi. This del square phi is equals to del square phi plus dou phi by dou T of del dot A is equals to minus rho by epsilon naught we have got, and another equation which we have got is this equation. Now here what we have to do is we have to use the Lorentz gauge transformations we have to use. So by using the Lorentz transformation, so we have Lorentz transformation we have. So here what we'll do is we'll write the Lorentz transformation, that is del dot A plus 1 by c square into dou phi by dou T, which will be equals to 0. So this equation we are going to be using, that is Lorentz equation. So by using this equation, we will substitute in this equation previously in this equation 2 and as well as in the equation 3. So this is equation 3 if you take. So in the equation 2 and in this equation 2, we have to substitute the Lorentz transformation. So if you substitute the Lorentz transformation, in this equation 2. So it will be del phi. We are going to get it as del square phi. Okay, del square phi minus 1 by c square is into rho square phi by rho t square is equals to, we are getting it as a minus rho by epsilon naught we are getting. So here we have it. The equation is del square phi plus rho by rho t of del dot t. So there if you substitute, so we are getting del square phi minus 1 by c square rho square phi by rho t square. This is one equation we are getting. And again, we will substitute in the equation 3 the same Lorentz transformation so that we will get it as a del square A minus 1 by c square into rho square A by rho t square is equals to, are getting it as a mu naught j you are going to get, because this entire term will be 0, so that we are getting del square A minus 1 by c square into rho square A by rho t square is equals to mu naught j. This term we are going to get. So this is one equation, say that this is equation number 4 we have. This is another equation, say that equation number 5. So these equations, this equation number 4 and 5, these equations represents the inhomogeneous equations. Okay, inhomogeneous equations. Um, we will call here that is in terms of vector potential and scalar potential, del square phi minus 1 by c square by dou square phi by dou t square is equals to minus rho by epsilon naught, one equation. Another one in terms of vector potential, that is del square a minus 1 by c square into dou square by 2t square is equals to mu naught j. These two are the equations of inhomogeneous. That is the terms whichever we have on the right hand side of this inhomogeneous equations are the source terms of the electromagnetic wave equation. So which represents the generation of this, means this one and this one represents the generation of the field. Okay, so these are two equations which we call it as the inhomogeneous wave equation. Now we will move to the what we call retarded potentials. So retarded potentials is nothing but so in these two equations, okay, in these two equations, in case of a static field is nothing but whenever the stationary charge is present, so whenever the stationary charge is present, in that case, we'll be calling the field which is producing, we call it as a static field, we are going to be calling. So if this is a static field, the condition which we are going to take it is if the static field, if you are having, if the static field. So in the case of the static field, so what will happen means, so these two equations will reduce this to the Poisson's equations. That means this equation will become del square phi is equals to minus rho by epsilon naught, and this equation which lead to del square A, which will be equals to minus mu naught j here. So this is one equation. It is going to be get, and another equation, this one, by taking the condition that in the case of the static field, these are going to be reduced to these two equations, which we call it as what we call a Poisson's equation. We call here. Okay, so we call it as a Poisson's equation. So these Poisson's equation, they may take the solution these two equations, so which we are going to be right here for the solution of this equation as a These two equations, del square phi minus rho by epsilon naught and del square A minus is equal to minus mu naught J, we will be calling it as the Poisson's equation. So these are having solutions. One equation you are going to get it as a solution for phi you are going to be get, and another equation which you are going to get it as a solution for A you are going to get. So those solutions which we have like phi value and a value. So these we will be calling it as a solutions. So generally the solution for this we can write it as a phi value. So the solution for the phi, which in terms of r we are going to write that we are going to get it as 1 by 4 pi epsilon naught integration over a volume we are going to get generally to r dash by r is equals to r dash. R is equals to R dash into D cube. Otherwise, simply we can write it as a volume also. This is one equation we are going to get. And for this one, we are going to get it as A is A of R. We can call A of R is equals to, which is a mu naught by 4 pi integration on a volume. Generally, you are going to get A R dash by R is equals to R dash, and which is in the volume D cube. We are going to get. Okay. So these two are the solution 5 and A are the solutions which we have. So generally, what you are going to take is we are going to take any electromagnetic wave which travels with the speed of light. It is going to be travel. So therefore, to determine the potentials in this case, the time varying fields at a point P from a source Q as we are going to be taken. In this case, we are going to be consider the condition of the wave of some what we call a retarded time we are going to be considered. The retarded time we are going to take it as a TR we are going to be taken. And this TR retarded time is nothing but the time taken by the wave to travel from one point to another point, that is from the source point to the field point. So suppose if you take the source point as the Q if you are taking and field point P if you are taking, it will travel from Q to P. So that time whichever it is taken as a retarded time we are going to be called here. So now, as we told that whenever it is moving from one source point to the field point, the time taken to travel, which we will be calling it as a retarded time we are going to be called, and this retarded time is known as retarded time TR we are going to be taken. That TR we are going to be take here. That TR we are going to be written as a TR is equals to this TR value, which will be equals to actually the time to travel from one place to another place. We can write it as a T is minus R is equals to R dash by C. We are going to write here. Okay. And the distance traveled is R minus R dash. So generally we are going to be taken. So if we do that, we are going to get the generalized equation of this phi of RT with respect to distance traveled, which we are going to get it as a 1 by 4 pi epsilon naught you are going to be get. So in terms of this rho R dash TR we are going to be get and R minus R dash. So over a volume generally we are writing here dq R dash. So similarly we'll write A of RT. So this A of RT is equals to this mu naught by 4 pi integration J of R dash TR we are going to be and R minus R dash into dq r dash we are going to be calling. So these equations phi of rt and a of rt, these equations we will be calling it as a retarded potential we are going to be called here. Okay, so this one is a very important equation, retarded potentials. So which they may ask what we call as short questions they may ask. So this is about the inhomogeneous wave equation and as well as this what we call retarded potential we are going to be called here. Now we'll move to another equation, that is field of a localized oscillating source. Okay, so generally most of the radiation systems which are called as a localized oscillating source, that is nothing but the system of electric charges and the currents that generate these electromagnetic waves which are propagating outward through a free space. Okay, so to find the fields at a distance r away from the source, so we'll take a break down the oscillating source into frequency components, applying the Fourier analysis and obtain the final solution of the superposition. So with the help of those, we can get the values of these values we are going to get. So that is not required, but we require this mainly the electric dipole approximation we are going to be with. So electric dipole, which is a very important question. This one is electric dipole. Okay, so in order to get this electric dipole equation, so what we will do is we will take the what we call the integration of the equation we are going to be taken. So that is nothing but we'll take the exponentials in the equations in the equation we are going to be taken. So generally that will exponential will be in the form of like e power x is equal, so we can write it as e power x naught to n. It will be written as 1 plus x plus 1 by 2x square plus and so on you are going to get here. So here, so by taking this equation into consideration, we will write the as we have written previously the solution. Previously the solution which we have written e of x rt we have written. So this if you apply for a distance, so that is small distance if you apply, so we can write it as a of x comma t is equal, so we can write it as a mu naught by 4 pi exponential of I kr minus omega t by r, and the integration over a volume k of x dash exponential of minus I k r into this r means r dash we have to write. So x dash over a volume d cube x dash we are going to write. So here in our RHS, whichever we have this exponential term e to the power of minus ik, this value we are going to be expand by using this equation we are going to be expand. So by expanding this and by substituting in a equation that is in a monopole equation, if we substitute, so finally we will get the equation as an electric equation which we are going to get as a of xt is equal. So by solving all this, we are going to get it as a of xt is equal to, we will get it as a I omega mu naught by 4 pi and exponential of I k r minus omega t by r you are going to get. Okay. R you are going to get, and this integration part which you are going to get as a x dash a row of x dash dq, that is what a volume we are going to get. So from this, if you solve, we are going to, for electric dipole radiation, the rho value which you are going to get it as a electric dipole radiation, that is integration x dash a row of x dash dq x you are going to be get. Okay. So by solving these, by taking the vector potentials and all those things, so even we can get the magnetic field radiation we are going to get, that p value we are going to get. So p value generally you are going to get like a mu naught ck square by 4 pi k cross p e to the power of k r minus omega t by t you are going to get. So from that we can get the e value. So this is what the what we call electric dipole radiation we are going to be called here. Okay, so this is what we have. So this is one of the electric dipole radiation. So next we will move to another important topic. So because I'm skipping some of the topics here because we required important topics. So first we will see the what we call magnetic dipole radiation we are going to be see here. So the magnetic dipole radiation is very important. So here in order to get this magnetic dipole radiation, okay, so we will take next we'll move to the magnetic dipole radiation. So in order to get the magnetic dipole radiation, so right here, the magnetic dipole radiation. Magnetic dipole radiation. In order to get the magnetic dipole radiation, we will be defining first of all the magnetic moment we have to define. So that magnetic moment vector we can write it as m is equal to I into A we can write. Okay, m is equal to I into A. That is a magnetic moment vector. So here I is nothing but the current and A is nothing but the area vector here. So generally this we can write this as half into integration surface integral r cross I dl we can write here. So this overall we can write it as half of integration or in terms of j we are going to write r into j we'll write into dx we'll write here. Okay, so this is m is equals to value is equals to half into integration r j dx we have. So here we'll take this equation and as well as the another equation we are going to take and we'll substitute this expression whichever we have got in the vector potential equation we are going to be substitute. So that equation will write here. So vector potential is nothing but which is A is equals to we have in this expression A is equals to some t, sorry, A of xt. A of xt is equals to we have like a minus mu naught by 4 pi as a total exponential of I k dot r minus omega t, k dot r minus omega t by r we have integration r we have. So here in this if we substitute 1 by r minus I k into x into m we have. So here is the equation which we have. So by using this equation for the magnetic field due to dipole radiation we have to use. So this equation A of xt whichever we have. So this equation, this is one equation we have, this is another equation. So these two equations we will use to get the magnetic dipole radiation we are going to be get here. So generally the magnetic dipole radiation that is we have a B of x comma t is equals to del cross A of x comma t we have. So this is the magnetic dipole radiation. So here in this case del cross in place of A of xt we'll write this entire equation that is a minus mu naught by 4 pi exponential of I k dot r minus omega t, okay, divided by r into 1 by r minus I k into r cross m, this. So here if you solve this equation, so we will get this as we are going to get it as a mu naught by 4 pi a square into exponential of I k dot r minus omega t by r into r cross m. Okay. So if you solve this, you are going to get this equation. That is mu naught by 4 pi k square into exponential of I k r minus omega t by r into r to r. This one is r into r cut. We are going to begin. So now what we have to do is we have to use the relation between the electric and magnetic field vectors to calculate the electric field due to the magnetic dipole radiation. So due to the magnetic dipole radiation, we have to calculate the electric field. So in order to calculate that, so what we will do is here we will take this value, that is del cross E, del cross E, so which will be equals to, we have from the equation as minus dou B by dou T. Okay, del cross E is equals to minus dou B by dou T. So this equation we can write it as a I omega del cross A, we can write. Okay, so we can write I omega del cross A, we can write. So therefore E is equals to, it will be, so here if you compare this and this one, so you are going to get E is equals to I omega A of xt, you are going to get I omega A of xt here. Okay. So now what we'll do is we will substitute the vector potential in the equations. So here and the previous equations we are going to substitute. So you get, if you substitute the vector potential, you will get E is equals to I omega into, that is dot minus mu naught by 4 pi, here we have. So exponential of I k dot r minus omega t by r into, already we have written this equation, by r minus I k into r cross m, we are going to get. Okay. So finally, if we solve this equation, we will get this E value, that is electric field due to a magnetic dipole. You are going to get it as a minus I omega into this mu naught would be there by 4 pi exponential of I k dot r minus omega t by r into r cross m. So here this E value you are going to get. Okay. So this is the value of the electric field due to a magnetic dipole radiation. You are going to get. And if you want to calculate the power radiated by this, if you want to calculate, the power will be given by P is equals to mu naught into C k to the power of R by 12 pi into mod of m square, you are going to get. So this value is the power radiated by this one. So this is the magnetic dipole radiation electric field, this equation, and this equation is the total power radiated by this is given by P is equal to this value. So this one is very important, magnetic dipole radiation. So even we can calculate the electric quadrupole approximation also. In order to calculate the electric quadrupole approximation, what you have to do is we have to consider a electric quadrupole we have to consider in the previous equation, and we have to substitute then vector potential also we have to take. Okay, one is electric quadrupole radiation, we have electric quadrupole we have to take, and vector potential we have to take. For the electric quadrupole, we will substitute E of xt value, and finally we will get the E value as well as this what we call that is electric field due to the quadrupole you are going to get, and similarly the total power radiated by the quadrupole also we can calculate. So then I'm not here. I'm not going to derive those quadrupole radiation electric field as well as this one, and directly I'm writing here. So the for electric field for a quadrupole radiation is given by E is equals to, you are going to have like a minus of I k cube by 6c into You have this mu naught by 4 pi and the exponential of I k dot r minus omega t by 2r you are going to get here. So in this case, into x into what we can x into q of x you are going to be. So this is the value of for what we call quadrupole. The electric field which you are going to get for quadrupole radiation is E is equal to this value you are going to get. Similarly, we can calculate the total power which is radiated by this quadrupole is given by P is equals to mu naught ck power 6 by 360 times of 4 pi 4 pi into q of x whole square. Okay, 360 into this 4 pi. Okay, 4 pi, this 4 pi. This is what the total power radiated. So among this electric quadrupole as well as magnetic quadrupole, these are magnetic dipole. Next we have is this electric quadrupole. So these are the electric fields which are given by the magnetic dipole and as well as electric quadrupole and their power radiated. So now we will take the what we call we have to calculate next topic. Next topic we'll see that is very important one, which is what we call this Leonard Wichardt potential. This is very important topic. Leonard, okay, Wichardt potential. Wichardt. Leonard Wichardt potentials. Leonard Wichardt potentials. So here, in order to calculate this Leonard Wichardt potentials, so we will consider a charge, electron of charge q, which is moving with certain velocity at the time t, and p is the point at that particular time. So in this case, we will be calculating the retarded time with reference to the position of the electron at a given instant of time we are going to be calculate. So for that, we have a picture we can draw here. So this is the origin at this point. Okay, so O is there. So now here, the trajectory of the charge, if you take here, so the trajectory of the charge. So this is the trajectory of the charge which we have. So now this is the source point if you consider. Okay, this is the source point if you consider. So from here to here, the distance is x dash we have. So this one is the source point. Okay, this is the source point which we have. And suppose if it is moved from here to here, so that is x dash to say that x dash at a time of t, x dash of t. So now we'll take this is the field point p which we have. So from here to here it is x minus x dash you are going to be have, and this value will be again x minus x dash of t. This is x minus x dash we have. So this value is x minus x dash of t we have, and from this to this we'll be taking it as a x we are going to be taking. Okay, so we have considered an electron of charge q which is moving with certain velocity, that is dou x by dou t. Suppose if I take, so at a time t if you are taken, so this p is the point at present time t here. Okay, so this is the p is the point at present time. Okay, so in this case, the retarded time with reference to the position of the electron at a given time, which is shown here. So now, so therefore, we will take the retarded potential. So we'll write the retarded potential. So that retarded potential, already we have written this pi of x comma t, which will be equals to 1 by 4 pi epsilon naught times this integration rho of x dash t naught is the time which we have taken, and delta of t minus x dash by c divided by the distance, which is this x minus x dash with respect to time dt naught, and the volume is dq x dash we have. Okay, so this is the retarded potential which is given by. And now what we'll do is we will replace the charge density in this retarded potential with the rho of xt. Rho of xt, which will be equals to q into delta of x minus r t for a moving charge q with respect to r, which is allowed to vary with respect to the time delta function accounts for this one. So this equation will becomes phi of xt, which will be equals to 1 by 4 pi epsilon naught times integration. So this 1 by 4 pi epsilon naught times. So if you replace that rho with delta x minus x naught, and this will becomes delta of time period is t naught minus of t minus x minus x naught by c, okay, divided by x minus x naught into d t naught dq x. Okay, what we did is we replaced the charge density in the retarded potential with the rho of xt is equals to q into delta of x minus r of t we have replaced for a moving charge q. Okay, so now for an electron, the retarded potential in terms of the delta function. For an electron, the retarded potential in terms of delta function, we can write this above question as phi of x comma t, which will be equal to, it will be equal. Now, this equation for an electron, the retarded potential in terms of delta function we are writing here. So this will become q by 4 pi epsilon naught integration delta of, okay, so it is t naught minus t minus x naught by c by x minus x naught into dt naught we have. Okay, so this is for an electron, the retarded potential in terms of the delta function we are writing here. So here, to utilize the properties of this delta function, let us introduce a new variable, which is a t double dash we are going to be taken, the new variable t double dash, which will be equals to t naught minus t plus x minus x naught by t here. Okay. So in place of this t naught minus t plus x minus x naught by c, we will be writing t double dash. So this equation, if you differentiate, so that means dt dash, if you do, so you are going to get what we call, if you differentiate this equation, so this differentiating equation, we will get dt double dash, which is equal to dt naught minus, means here minus, it is going to become plus, it will be 1 by c d by dt naught into x minus x naught into dt are going to get. So now, if you solve this equation, you are going to get this dt double dash, which is equals, we are going to get it as, if you solve this equation, we will get it as a dt naught plus into 1 minus beta into r by r, you are going to be get here. So here, this r, that is nothing but r value is equal to mod of x minus x naught we have taken, and in place of beta, it is v by c you are going to be have. Okay, so by using this equation, that is dt double dash, and we will substitute in this equation. Okay, in this equation we will substitute. So if you substitute in the phi equation, if you substitute in that equation, if you substitute, we'll get phi is equals to, that is phi means phi of x comma t. So phi is nothing but phi of xt here. So this phi of xt. So this phi of xt, we are going to get it as this q by 4 pi epsilon naught integration delta of t double dash divided by r minus beta dot r into dt double dash are going to get. Okay, so this what we have did is dt double dash value we have substituted in the previous equation, we have substituted, and we are getting this phi of x is equals to q by 4 pi epsilon naught into delta t double dash by r minus beta dot r into dt double dash you are going to get. So in if you take the specific value, that is nothing but for t double dash is equals to 0 if you take, and another one, that is 1 minus beta dot r is equals to k if you take. So we get this phi of x comma t, phi of x comma t, which you are going to get it as 1 by 4 pi epsilon naught into this q by kr, which is a retarded potential. Okay, so this value we are going to be get, and similarly we can find out the value of the vector potential for the current density G is equals to rho V can be written as A of R comma, sorry, A of x comma t, A of x comma t, which will be equals to 1 by 4 pi epsilon naught q by kr for retarded potential. Okay. So these two equations, that is phi of x t is equals to 1 by 4 pi epsilon naught and a of x t value is equal to 1 by 4 pi epsilon naught, these are called Lienard-Wichard potentials we are going to be called. We'll be calling it as what? Lienard-Wichard potentials we are going to be called. So these Lienard-Wichard potentials are the retarded potentials for the relativistically moving charge, which depends on the velocity of the charge, and it is independent of nature of the charge distribution. So this is what the Lienard-Wichard potential. So this Lienard-Wichard potential is very important question. Okay. Next, we will see another topic, which is center-fed antenna. Center-fed antenna we'll see here. So in this center-fed antenna, linear antenna, we will consider it. Actually, it is consisting of two thin wires of a length half, that is a d by 2 orientation along the z-axis you are going to be have, and a small gap at the midpoint you are going to be have. So we draw that one. So next we will move to this center-fed linear antenna. central fed antenna or linear antenna, which will radiate permanent radiation. We will draw this central fed linear antenna here. Here like this. So in this direction, you'll have a d by 2. Again, in this opposite direction also, you'll have another d by 2. So this is in the opposite direction. We have this is minus d by 2. This is what we have. So here. So here it is d by 2. Okay. So here, this is the point E. This angle is phi. We have this angle is theta. This is the direction. This is y direction. This is x direction. Okay. So now we have the coaxial. What we have considered is here we have considered a center-fed linear antenna. Okay, center-fed linear antenna which consisting of two thin wires of length d by 2. One is above d by 2 and then is another below d by 2, which are orienting along the z axis. So in this direction they are orienting. Okay. So at this point we have the midpoint, which is the origin. So the antennas used in radio or in television transmission are not short compared to the wavelength of the radiation they'll transmit. So hence the current in the antenna cannot be constant. Okay. So here we assume that the current density is varying harmonically with space as well as time. So the current at the each end of antenna is zero and the standing waves are high at the nodes we are going to be having. Okay. So now what we'll do is we will write the current density value. So the current density is given by J is the J of RT here, we'll write here. J of RT, which will be equals to Z of I naught exponential of I omega T sine of KD by 2 minus K of Z into dou X dou Y. Okay, the current density is this one. And here the current at the gap, which is I, we will write here, I of t, so which will be equals to I naught exponential of I omega t, exponential of I omega t sine of k d by 2 we have, sine of k d by 2 we have. So this one is one equation, that is the current density, and this is the equation for the current at the gap we have. So we'll use these two equations, and so by using these two equations, the vector potential at the point P we can write here. So already we have seen the vector potential, that is A of x comma t. Okay, A of x comma t, so which is equal to actually naught by 4 pi mu naught by 4 pi integration j of x dash dr by r minus r dash into d cube of x that we have. Okay, so this is the value we have. So here we have j of uh, x dash dr value is there. So that is whichever from the equation 1, we have j of rt value. Here we will substitute and we will get the value of what we call this a of xt. A of xt, if you substitute and if you write, you'll get it as mu naught by 4 pi z I naught, because we here in this place we are substituting this equation 1, we are substituting so that we are getting integration exponential of I omega t into, you are going to get it as a sine of kd by 2 minus k of z into dz by r minus z, you are going to get. Okay, so this is the value of A of xt, that is the vector potential at this point P we are getting. Okay. Here we'll solve this A of xt value. This is the vector potential. So we have substituted this vector potential A of xt is equal, so we have got it as a mu naught by 4 pi, this value, z of I naught exponential of I omega t sine of kd by 2 minus k of z by r minus z. So actually it should be mod of this one we are going to be get. So this value. Okay. So now what A of xt vector potential we have got. So you take this as some equation number 3 you take. So now if point P, the point P here, this point P is far away, then we will write this. The condition here you should take is if the point P, okay, the point P is far away, okay, that is the mod of r minus z value is approximately equals to r minus cos theta. That is, if the point P is far away, we will approximately get the value of r minus z equals r minus cos theta, and the denominator is just r you are going to be get. So therefore, a of xt value here we can write in this equation will change this into a of x comma t, which will be equals to you are going to get it as a mu naught by 4 pi z, and this I naught will be there. That exponential term we can take outside, so that it will be exponential of I omega t into exponential of I k dot r by r here v, and the limits are from -1/2 to +1/2. That is d by 2 is nothing but here we are taking it as a 1/2. That will be sine of kd by 2 minus of kz, and the exponential of minus ikz cos theta into dz you are going to get. So this one, if you do the integration and if you substitute, you'll get it as a mu naught z by 4 pi. It is constant, and the I naught as is will be there e to the power of I omega t. So this is final, okay? I e to the power of I omega t into e to the power of I k r by kr, and this entire integration, if you do, you'll get it as cos of kd by 2 cos theta minus cos of kd by 2 divided by sine square theta you get here. Okay, so a of xt is equal to, this is the value which we are going to get. Let it take it as equation number 4. Previously we have considered as 3. This is equation number 4 which we have. Okay, so this is the a of xt value which we have derived. So then we have to find out the b value also. So in order to get the b value for this one, so we have the formula b is equals to del cross a. Okay, b is equals to del cross a we have. So here we can write b value is equal to, we can write here as b is equal to I k and cap, that is unit vector class a we can write. So from that we can write b mod value, we can write it as a half k square a square sine square theta we can write here. So now if you substitute this value half into k square a square sine square theta in place of a here, so already we have derived the value of a, we have derived in the previous equation. So we will get this elemental value as some z into I naught. This value we are going to get it as z into I naught by 4 pi square r square into, and this entire value cos of kd by 2 cos theta minus cos of kd by 2 divided by sine theta you are going to get here. Okay, so this value you are going to get. So again, this is a b square value you are going to get. Similarly, we can get the time average rate of power flow, which is nothing but the pointing vector. From pointing vector we can get that value. So that is mod, sorry, average pointing power flow we can say, which is equals to half of E cross B, which is this one. Okay, E cross B. So which is actually, it is z by 2 by mu naught b square you have. So this value from the previous equation, whichever we have got the b value. So b value if you substitute here, so you'll get this as equals to under root of mu naught by epsilon naught by 2 into z I naught square by 4 pi square into r square mod of entire value. So that is cos of kd, right here cos of kd by 2 cos theta minus cos of kd by 2 whole square. Means here sin theta will be there in the denominator and the whole square is whole square will be outside. So this is the average rate of power flow you are going to get. So if you want the average radiated power into the unit solid angle, if you want, we will get that as by dp by d omega will get here. dp by d omega. So this value again, if you solve, you are going to get as a 4 pi r square into this average Poynting vector s by 4 pi, that is r square s of z you are going to get. Okay. So that value dp by d omega, you are going to get it as a mu naught by epsilon naught under root of mu naught epsilon naught by 2 into z I naught square into cos of kd by 2 cos theta minus cos of kd by 2 by sin theta whole square you are going to get. So that is the angular distribution of a radiated power depends on the value of this cos of kd by 2. This value it is going to be depend, and its value is 0 when theta is equal to 0. Why? Because cos of 0 value will be cos theta value is equal to 0. Otherwise, theta value is equal to pi. The cos of kd by 2 value will be 0. So, which dp by d omega for a full wave antenna, you are going to get one value that is under root of mu naught epsilon naught, under root of mu naught epsilon naught 8 pi I naught square into cos of pi cos theta plus 1 by sin theta whole square you are going to get. So similarly, for a full, why we are getting that means for a full wave antenna, d value is equals to lambda you are going to be have, and for a half wave antenna, it will be d is equals to lambda by 2. You are going to get. So we will get the radiating power for full wave antenna we can derive. So the full wave antenna, we'll write here radiating power, which is given by p value. We'll write here. We'll write the dp by d omega for full wave antenna and as well as the for the half wave antenna. We have written, and similarly, the total radiated power which is given by this P for full wave antenna is given by half into under root of mu naught by epsilon naught by you get it as 8 pi into I naught square by r square integration cos of pi of cos theta plus 1 divided by sin of theta whole square minus r square sin of d theta d phi. Okay. So if you do this integration and if you get this value is equals to under root of mu naught by epsilon naught by 8 pi into I naught square integration from 0 to pi cos square pi cos theta by sin theta into d theta. Okay, so this is the radiating power, which is equals to mu naught by which is equals to under root of mu naught epsilon naught by 8 pi into I naught square integration from 0 to pi, value is 0 to pi cos square pi of cos theta by sin theta into d theta. This is the total power radiated for full wave antenna. Similarly, if you want to get the total power which is radiated for half wave antenna, here simply what you have to do is you have to do 1 by 2 times we have to do. That is half wave antenna lambda by 2 we have to take. So that power radiated for half wave antenna will get it as equals to under root of mu naught by epsilon naught by 8 pi, and this is I naught square into integration again from 0 to pi. You are going to get here, you will get the cos square of pi by 2 cos theta you will get divided by sin theta into d theta. So this is the value of power radiated, that is the total power radiated for the half wave antenna. So we have both the full wave antenna and the half wave antenna power radiated, which we have here, right? So here the total power radiated of we have seen the magnetic dipole as well as the electric dipole. So that is the total power radiated by magnetic dipole and electric quadrupole, which we have seen. And similarly, we have calculated the linear recharge potential, which we have got it as a phi of x t is equals to previous 1 by 4 pi epsilon naught by into q by k we have got. And similarly, the A value also we have got A value, that is vector potential A of x t is equals to mu naught by 4 pi q by c k we have got. So similarly, we have calculated the total power which is radiated by the full wave antenna, which we have got. This is the equation, that is under root of mu naught epsilon naught mu naught by epsilon naught by 8 pi into I naught square, the integration 0 to pi cos square of pi cos theta by sin theta into d theta. Similarly, we have got the total power which is radiated by half wave antenna, which is equals to under root of mu naught by epsilon naught 8 pi I naught square integration from 0 to pi, and this value is cos square of pi by 2 cos theta by sin theta into d theta. This is the value of the half wave antenna power radiated. Okay, so this is what we have in the case of the electromagnetic radiation. So similarly, we in this next chapter which we have is the radiating by moving charges. So radiating by moving charges means in this case again you are going to get whenever a charge is moving, we will get this typical radiation by a charge moving at low velocity you will get, and similarly radiation by charge moving with a collinear velocity and acceleration, and similarly the radiation by charge moving in a circular orbit. So in different cases we'll get whenever the charge is moving, fields of a moving charge will get, and similarly the radiation by charge moving at low velocity. So for that also we will calculate this radiating power dp by d omega. So generally you are going to get it as a s r square you are going to get in that case. Similarly, we will calculate the radiation by charge moving with a collinear velocity and acceleration. So for that also we can calculate the this power electromagnetic power which is radiated. So in that case, generally we'll get around mu naught q square by 6 pi c beta square by 1 minus beta square you get. And whenever a charge is moving in a circular orbit, how much power it is going to be radiating, that is also we can calculate. So in that case, we will get this P is power, electromagnetic power, which is emitted in a direction. We are going to get it as a P is equal to 2q square by 4 pi epsilon naught into beta square by 3c into 1 minus beta square whole square. You are going to be get here. So that is what we'll get.